So the second lesson that we're going to look at this week is objects on forces with objects on inclines. I'm going to tell you up front, this is the section that students tend to find a little more challenging. I hope I've addressed some of that by thinking about vectors in the last lesson. We're going to really want to be really careful with our diagrams. We're going to have to do some real thinking, and we've got a lot of different pieces in them. The math is no more complicated than in the last lesson, but it will require you to do a good little bit of thinking. If you don't understand it all right off the hop, next week we're going to spend a little bit more time on it, and we're going to look at doing some lifting, and that will pretty well finish our section off, and we'll be ready to do an assessment on this section. All right, so just as a quick recap, force is not equal to weight in these two scenarios. Why? I said force is not normal force. Normal force is not equal to the weight. Why? Well, weight is the force of gravity. So weight is pulling downwards. So this is our Fg, or our weight. In this case, we have two upwards forces. We have normal force and an applied force. Because we have two upwards forces balancing out the force of gravity, normal force won't be equal to gravity. Normal force is going to be less than gravity in this particular scenario. In this one, we have somebody pushing downwards, which means we have an applied force down. Normal force has to balance out both of those. So in this case, our normal force will be greater than the force of gravity. This is more friction. And this one is less friction. Okay, so we were just thinking about how angles come into play. I want you to remember that normal force is not always equal to weight or not always equal to the force due to gravity, because for all of the questions we're going to look at today, that will be the case. So now what we're going to do is we're going to look at a scenario where you're loading something onto ramps, something that's fairly commonly done. The last question I'm going to ask you when we finish up this lesson is it worth a lift kit on your truck? Okay, so which truck is going to be best for the job? I'll let you think about that one. I know cool lifts on trucks look really cool, but from a physics perspective, is it actually cool? We'll find out. So here you have an individual, they're pushing a crate up a ramp. So you can see their applied force diagrammed in as the red arrow. How will normal force and the weight of the object be connected? So what we're going to do is we're going to just do a little bit of diagramming first. So if they're pushing on an incline, we have an angle. Okay, so they're pushing up at an angle. We know gravity, it doesn't matter where you are, gravity always pulls towards the center of the earth. So gravity is always going to be straight down. That's supposed to be a vertical line. Let's see if I can modify that a little bit. Gravity is always going to pull towards the center of the earth. So there's our force of gravity. And you're probably wondering why I'm erasing things. I'm not, I should be looking at where I wrote things in my notes first, but I'm just thinking as I label my information, sometimes I'm going to want to write around it. So gravity is going to pull straight down towards the earth, but normal force will be perpendicular to the surface. So that means, okay, if my surface follows roughly that line, my normal force is going to be 90 degrees to that. So it's going to be straight up this way. And I find it very hard to get straight lines with this lovely tablet I have. So this is our normal force. You'll notice the force of gravity is not exactly opposite to the normal force. But if we were able to break gravity into components, We could have one portion of gravity holding this crate to the surface. We know that that happens. And the other portion of gravity is actually working towards pulling that crate down the surface. Okay, and then the angle here will always be equal to the angle of incline. So those two angles are equal. So the angle closest, I'll put it as the angle closest to the center of your box that you're diagramming will always be equal to the angle of inclination. So how will normal force and the weight of the object be connected? The normal force is going to be equal to the force of gravity, but only the component perpendicular to the surface. And this is how I abbreviated. This little T symbol means perpendicular. So this means we're going to have to use vectors, a lot like we did in our last lesson. Remember the last lesson we were pulling at an angle and normal force was impacted by that perpendicular component of my pull or my push? Well, in this case, gravity has to be broken into a perpendicular and a parallel component. So just to summarize everything all together for you, so normal force will be equal to the perpendicular component of gravity. I'm going to sketch my diagram again. Just bear with me in my poor sketching. So force of gravity will go straight down. There we go. I'm getting, I was doing really well with having a straight line there for a second. So this is my force of gravity. Normal force is going to be straight up from the surface. Try to get that. Here's my normal force. And then here we have our two components for gravity. So here's my angle. And there's my other angle. All right. If you're kind of wanting to visualize this is a really nice example to do simulations. I don't have a good simulator that doesn't require Flash, and I'd rather not use one that requires Flash. Now let's see if I can get you a video explanation. Sorry. That shows you these forces, and I think I may have one available. But often in class, what I'd use is just a ramp. I'm looking at, as I move that ramp steeper and steeper, what happens to an object that's on it. And it helps us show how the components of gravity switch and go from being more in the parallel to the surface, more of the force of gravity being perpendicular to the surface to more of the force of gravity being parallel to the surface. So that's one of those things you can kind of play with it at home. Just visualize what happens if you put something on a ramp and how it slides. Just think of it sliding downwards rather than maybe pushing upwards. All right, so we have our components. I just want you to think about how we calculate the components. So this is my force of gravity, perpendicular. It's going to be equal to my normal force in this scenario. I know he's pushing at an angle in the picture, and you just learned that pushing at an angle is going to cause, but our arrow's drawn exactly in the same direction as the surface. So perhaps not a perfect picture given the last one, but I'm assuming there's no extra force. We could complicate things with that, but I don't think we need to do that for these angles. That would give us angles and angles in angles, and that's going to cause a little bit of trouble. If you really want a challenge, I'll give you one. So our force of gravity perpendicular, this is adjacent to the angle, so that means it's going to use cos. So the perpendicular force of gravity is always going to be equal to the total force of gravity times the cosine of the angle. Okay, so that's our FG perpendicular, which will be equal to your normal force. So if you want one to just kind of put in a cheat sheet for quick reference. The parallel force of gravity is what pulls it down the ramp. That's this force here. This is the opposite side, so it's going to use sine, SOH. So force of gravity parallel is going to be equal to the force of gravity times the cosine of, oops, I just wrote cosine, I meant sine. So it's the sine of our angle. okay? And then the force of friction, the direction of the force of friction is going to depend if the box is sliding up the ramp or down the ramp. In this case, if we're pushing the box up the ramp, the force of friction would be downwards. If the box is just sitting on the ramp and gravity is pulling it down, so there's no other push, it's just gravity pulling it down, then friction is actually going to be up the ramp. So friction is going to depend on what direction it would move if it moved, and we're going to want to kind of stop and think about that and apply it depending on the scenario. So hopefully that kind of gives you a good visual. Hopefully that it helps you understand how those vectors are going to break apart. And now we're going to do I only have 2 example questions, I think. Yes, I only did 2 example questions because these questions do take a little longer to solve, and I don't want to overwhelm you with too long of videos. So example 1, a wooden crate that weighs 800 newtons is on an inclined plane. And please, let's assume this is 800. We'll do 2 significant figures. Sometimes I haven't necessarily included that in the question. So it's on an inclined plane with an 18-degree angle. The coefficient of friction is 0.55. I want to find the normal force. I want to know the parallel force. I want to know the frictional force. So you'll notice this is broken apart into pieces that allow you to calculate successfully. We call that scaffolding, when we break it apart so that it guarantees success for students. Sometimes you will have more scaffolding than others. At this point, it makes sense to have maximum scaffolding. So we have our inclined plane, and this is 18 degrees. We have our box, or a crate, sitting on it. Now you'll notice the crate weighs 800 newtons. This is the force of gravity. You do not have to do any other calculations because it's already newtons. Notice I didn't say it has a mass. I said it weighs. So that actually saves you a calculation. So we can actually put the force of gravity in. And there's our force of gravity. Let's see if I can adjust my tablet so I can get less cockeyed pictures. So our force of gravity is down. Oh, me and I keep wanting to put the force of gravity next to my arrow on that side, and I need to move it so that I can write around it. So force of gravity is equal to 800 newtons. There. Normal force is going to be up from the surface. And then we have our components. The normal force is equal to Fg perpendicular. How do we calculate that? Well, we just had that in our last slide. So this is going to be equal to the force of gravity, 800, times the cosine of 18 degrees. 800 times the cosine of 18 degrees gives us 761 newtons. And that's our normal force. All right. Now, this one is our force of gravity that's parallel to the surface. So it's pulling that crate down the ramp, assuming I'm not pushing it. So force of gravity parallel is just going to be 800. We change from cosine to sine. Sine at 18 degrees, which gives us a force down the ramp of 247 newtons. Okay, so we have all of that. We want to know what the friction force is. So we have the force, I'm going to put it this way, force of gravity parallel is pulling down the ramp. So that means my force of friction would push the box up the ramp. So the force of friction is just equal to mu Fn, which is equal to 0.55 times normal force of 761, which is equal to 419 newtons. Okay? And this is equal to, I'll put it just over here so we can see it. Okay, so I've just I've separated the parallel and sketched it in just to help us visualize what would happen. D says, would the box slide down the ramp? So the parallel component of gravity is pulling down the ramp with 247 newtons, but the force of friction is up the ramp at 419 newtons. This will not slide. Friction is greater than the force of gravity. So no, friction, it won't slide because the force of friction is greater than the force of gravity parallel with the force of gravity that's pulling it down the ramp. By the way, if you're the less than or greater than signs, I used to always struggle with which one means less than and which one means greater than, and little tricks that work. The mouth always eats the biggest number. So when I use these symbols, if you're second guessing and you're going, oh, what does she mean by that symbol? Remember, it's like a Pac-Man. He always eats the biggest guy. Okay, so that'll help you. That'll help you if you're one of those people like me that that flips things around a little bit. So the box won't slide because the force of friction is greater than the force parallel. Question E is the tricky one. How much force would be needed to push the crate up the ramp? So when we're pushing it up the ramp, I'm going to redraw it and I'm going to isolate just the information that we want. So I want to move the crate up the ramp. So there's going to be an applied force up the ramp. Notice friction is going to pull down the ramp now because it's opposite the direction I'm moving. So here friction was up the ramp because I wanted to know would it slide down, so the motion was down. But now when I want to push it up, friction stays the same in size, but it switches directions. And then the force of gravity, Fg parallel, still pushes down. So I know my applied force has to be greater than the sum of these two. So how much force would be needed to push the crate up the ramp? Well, I would need a minimum of 240, I would have to overcome 247 newtons down the ramp, plus I'd have to overcome the force of friction, which is 419 newtons, which gives me 666, devilish question, 666 newtons needed. And that would be minimum. You would need at least that. You may need a little bit more. Okay, so that would be the force to push the crate up the ramp. But just one of those little things, the force of friction changes direction. I just put its opposite, the force applied, because the force applied is usually the direction of motion. Okay, so not complex. I mean, it looks a little messy, but when you stop and think about it, all of the pieces are exactly the same as we've had before. It's just that we got to use sine and cosine. That's the only difference. All right. So breaking things into pieces helps. And we're going to do one more question just to help you out. A crate that weighs 200 pounds is being loaded on a ramp with an incline of 28 degrees. The coefficient of friction is 0.24. How much force would be needed to lift the crate without a ramp? How much force is required to push the crate up the ramp at a constant velocity? You might know where I'm going with this question. This is one of those. Okay, I know you're not going to calculate it, but how does the physics affect actually what we do in real life? So you've got a 200-pound crate. One of the things to watch for first in this question, hopefully you noticed that I've given you pounds. If you didn't notice I've given you pounds, well, it's probably a good thing I'm going over this question. Convert pounds to kilograms. We have to use kg. I figured we haven't done anything where I've thrown in a weird unit. It was time. So 200 pounds to kg. There are 2.2 pounds in 1 kilogram. So we're going to divide by 2.2. How I remember? I know 2.2 is the magic number. And I know that if I step on the scale, the kg number always looks better than the pound number. So I know kgs are less than pounds. Memory tricks work. They help you out. So that's 90.9 kgs. It's 2.2 pounds in a kilogram. So we're going to want to use 90.9 kgs instead of our 200 pounds for our question. So just one of those little extra twists to throw in. Now we need to draw. Well, first of all, how much force would be needed to lift the crate without a ramp? So if I'm just lifting the crate without a ramp, I want to lift it up. How much force is it going to take to lift it? Well, I have to apply a force that's equal to or greater than the force of gravity. So I need to know, well, what is the force of gravity? So Fg is going to be equal to 90.9 times 9.81, which is equal to 892 newtons. So I would need to have at least 892 newtons. That would move it at a constant velocity. If I'm lifting it and accelerating, it would need more than that. So we need a minimum of 892 newtons to lift. Make sense? We have to lift. We have to overcome gravity when we lift, so it has to be equal to or greater than. Now, what if we have a ramp? How much force do I need to push the crate up the ramp? Compare a good old comparison question. So here's my box on the ramp. It's 90.9 newtons. Whoops, not newtons, kgs. All right, force of gravity. We calculated as 892 newtons. We know that. And we know we're going to have to break it into components because this angle is equal to 28 degrees. So we know the angle in here is 28 degrees as well. I need to know how much gravity is pulling this down the ramp. I'm also going to need to know how much gravity is holding it on the ramp. So Fg perpendicular is going to be equal to 892 times the cosine of 28 degrees. It's not supposed to be a decimal after that cosine. Okay, times the cosine of 28. Putting that into your calculator, you should find that you get a value equal to 788 newtons. Now, here, this one, I don't have enough space, so I'll write it off to the side. Fg parallel, pulling it down the ramp, is going to be 892 sine 28 degrees, which is equal to 419 newtons. The perpendicular force of gravity is equal to the force normal. That balances the surface forces. It balances the forces that are perpendicular to the surface. Okay? That allows me to figure out my force of friction. So I'm pushing the crate up the ramp. So this is my motion. This is my force applied. So that means friction is going down the ramp. And we have this force of gravity that's down the ramp. We've already calculated that over here. This is 419 newtons. That's that component of gravity. Force of friction is going to be equal to mu Fn, which is equal to 0.24 times 788. Gives us a force equal to 189 newtons. So how much force is needed to push the crate up the ramp at a constant velocity? This means my F net needs to equal 0. So I want the force. What force would balance these two downward forces? Well, I have 419 newtons due to gravity plus 189 newtons due to friction gives us 419 plus 189. 608 newtons. Okay, so this is your force of gravity parallel and the force of friction. You'll notice the force needed to push it up the ramps, even including friction, is less than the force needed to lift the crate. Why do we use ramps? It makes work easier. It makes work easier for us. Because it makes work easier, I shouldn't say it makes work easier. It requires less force. Because it requires less force, it should require less exertion. Okay, so that's a really good example of think and apply. Now the final think and apply question, I like this one. You've got 2 work trucks available for you to use, and you only have 1 set of ramps. Okay. If you have a lot of heavy gear to load and you're loading it via ramps, which truck will require the least force to load and why? So if you don't allow your ego to get in the way, which truck would be the smartest one to pick? The very cool, extremely lifted, or the stock, much lower, less cool looking truck? We're assuming there's no major snowstorms you're competing with, and we're not doing huge off-roading. All right, we're going to leave those out. We're going to just say this is a day where either one will be quite suitable for the job. So are you going to look cool, or are you going to work smart? That's the real question. Well, let's think about what happens. And this is just thinking about what we just did with ramps. So here, my ramp is the same length. It's the same ramps. The ramps are going to have the same friction. I'm loading the same thing. If I'm loading the same things, I'm going to have the same friction. So I got the same objects. So it's not like I can pick different ramps. But you'll notice here, this angle is much smaller than this angle. How is that going to impact the forces? Well, let's think for a second. This is the force. So you have your ramp here. We know gravity is going to pull downward. So let's just sketch in gravity. So gravity is going to pull straight down. And we're going to have 2 components to gravity. And in this one, same thing. Gravity is going to pull straight down. And then we have our 2 components. Okay. In this case, we have more gravity pulling us down the ramp than in this case. So we're going to have more gravity to overcome if I use the higher truck. It's going to be closer to just lifting that box straight up. This one, we have a larger normal force, which means we're going to have a little bit more friction, but we don't have as much gravity to fight with. Now, assuming you have a relatively smooth ramp, the friction would be minimal probably compared to the force due to gravity. Okay? So the lower truck is going to mean we have less force that we have to overcome. You'll end up with a question to calculate that involves this later. I'm definitely going to give you a question that involves this particular scenario. It's an excellent, excellent question for summarizing. Do you understand what's happened in this section? But one way to prove that, yes, it's going to be easier to load the shorter truck than the higher truck is to make up values and say, okay, well, if the first truck gives me a 30-degree incline and the other one's a 45-degree incline, what would the values be? What if it was just a 10 Newton container? Because it's not going to really matter if it's heavy or light. The relative proportion of the forces is going to be the same. But you will find it will take you less force to load the lower truck than it will to load the higher truck. So perhaps looking cool isn't always working smart, as opposed to dealing with the lower track. Now, what made me think of this was as I was doing up the questions, don't ask me why, but U-Haul slogan about the lowest decks came to mind. And that's a really good example of inclines where a lower deck makes it easier for us to load. Technically, we could have shorter ramps, which would reduce the amount of friction that we would have as well. Um, Now, one of the things we're going to get at soon is we're going to look at how force and work are related. When we look at how force and work are related, that distance over which you lift is actually going to come into play in terms of how much work you're doing. But most of the time, we want to work smarter, not harder. So less force is better. The only place where that may not be true is if you're at the gym working out. And if you're at the gym working out, you work harder, not smarter. There's a reason why I don't go to the gym. All right, so that finishes off this section. So that leaves us, it's done here. So that'll let you finish up this section. We'll give you a question to submit that uses angles. See how long it takes me to either do a submission via SAM or I'm not 100% sure which way I want to calculate it for you to make it easiest for you to get quick feedback. But I'll have that up just shortly.